Picture more than $1 billion in finished Apple silicon sitting inside TSMC facilities, fully fabricated, technically complete, and still unable to move forward. According to reports, that is the situation. Advanced logic wafers waiting not for fabrication, but for matching DRAM from third-party memory suppliers before final packaging can proceed. Apple, TSMC, and any named memory supplier have not confirmed that account in the available material, so it should be treated as a reported claim, not an established fact. But even if this specific case is never confirmed, it captures something increasingly important in advanced semiconductor manufacturing. A finished wafer is not the same as a finished product. That distinction matters because the industry narrative is shifting. For years, the headline achievement was reaching the next process node and proving that a leading-edge chip could be fabricated at scale. Now, more of the risk appears downstream. Logic has to be paired with memory, integrated, packaged, and tested before it becomes something a customer can ship. If the memory is missing, late, or mismatched in specification, then even the most advanced logic simply waits. In that sense, the bottleneck is no longer necessarily at the front of the line. It can emerge after the most visible manufacturing step is already complete. That is why this reported Apple TSMC case matters beyond the names involved. It points to a broader pattern. Some of the most consequential constraints in AI hardware may now sit in the less glamorous coordination layers of the supply chain. The macro picture reinforces that idea. According to Omdia, the firm has raised its 2026 global semiconductor revenue growth forecast to 94.1% year-over-year. In the available material, that sharp revision is driven not by chip demand in general, but specifically by AI-related demand for DRAM and NAND memory. The source does not provide a detailed model, an absolute revenue base, or a regional split, so it is worth being careful with precision. Still, the directional message is hard to miss. AI demand appears to be pulling memory much closer to the center of semiconductor economics. For Asia, that is not a side note. DRAM and NAND production remain heavily concentrated in the region, especially in South Korea, and among a small number of major global suppliers. If Omdia's forecast direction holds, then memory capacity planning, pricing, and supply chain resilience become strategically important in the same way advanced logic capacity already is. The AI hardware story may increasingly depend not only on processors, but on whether enough memory can be produced, qualified, and delivered in the right form. That shift is visible in how major memory producers are positioning themselves. At FMS 2026, Samsung presented what it describes as an industry-first NAND design, V10 BV-NAND, a product exceeding 400 layers and achieved using wafer bonding technology. That is a concrete manufacturing milestone, not just a concept. It points to a specific architecture and a specific method for pushing density higher. Alongside that announcement, Samsung also introduced ZHBM and zNAND-O as next-generation AI memory architecture concepts. Here the distinction is important. V10 BV-NAND is presented as a named manufacturing achievement. ZHBM and zNAND-O are directional signals rather than confirmed commercial products with disclosed specifications or customer commitments in the available material. Even so, together, they show where competition in memory seems to be moving toward higher bandwidth, greater density, more advanced bonding approaches, and tighter integration between memory and compute. Because South Korea plays such a large role in global memory roadmaps, this matters beyond one company. It suggests that the next phase of AI competition may be decided as much by memory architecture and packaging strategy as by raw processor performance. Memory is not the only hidden layer becoming more important. According to reports, zNAND-O is partnering with NVIDIA to build more than 8,000 miles of new long-haul fiber optic routes across the United States to carry AI-related data traffic between major computing hubs. This is not evidence of an existing Asian trend, and it should be treated here as a reference case only. But it highlights another possibility the region may eventually have to confront. If AI workloads become more distributed across multiple facilities, rather than concentrated in a single site, then the ability to move large volumes of data quickly and reliably between locations could become a visible infrastructure constraint. That possibility broadens the AI investment lens. It is easy to focus on chips, servers, power, and data center construction, because those are the most obvious pieces. But interconnection may matter more as systems scale. The open question for Asia is whether similar high-capacity network build-outs begin to appear in markets such as Japan, South Korea, Taiwan, Singapore, or India, as regional AI infrastructure matures. If they do, that would suggest the bottleneck is spreading from silicon and packaging into the networks that link compute clusters together. There's also a less physical but equally important layer forming around AI deployment: governance infrastructure. Under the EU AI Act, Article 50 transparency obligations became enforceable on August 2, 2026. In the available material, these rules require disclosure when users are interacting with an AI system, and mandatory labeling of synthetic content as AI-generated. On the surface, this is a European regulatory development. Operationally, though, its reach may extend much further. Asian AI developers, cloud platforms, software vendors, and digital service providers with EU-facing products may need to build disclosure interfaces, labeling systems, and documentation processes directly into how their products work. That changes the nature of compliance. Transparency is no longer only a legal review at the end of product development. It starts to become part of product architecture itself. In practical terms, that means governance requirements may shape workflows, interface design, and system behavior from the beginning, not after deployment. The final signal is different again. It is not about engineering capacity or regulation, but capital access. Vietnam is widely expected to be upgraded by FTSE Russell from frontier market to secondary emerging market status in September 2026. That remains an expected outcome, not an officially confirmed one, and it should be framed with that caution. Its relevance here is indirect, but still meaningful. A classification upgrade of that kind can influence portfolio eligibility, benchmark inclusion, foreign investor participation, and overall market liquidity. For a country whose role in Southeast Asian manufacturing and broader supply chain realignment continues to grow, greater capital market visibility could gradually improve the financing backdrop for industrial, logistics, and infrastructure development. It is not a direct technology catalyst on its own, but in a region where supply chain expansion depends not just on factory plans, but also on funding depth, market access and liquidity are part of the technology story. Taken together, these 6 signals describe the hidden layers beneath Asia's technology narrative. The first is that memory availability can delay the conversion of finished logic wafers into shippable products. The second is that AI demand may be pulling DRAM and NAND into the center of semiconductor economics. The third is that memory design and manufacturing method are becoming strategic battlegrounds in their own right. The fourth is that distributed AI systems may eventually require more network capacity between facilities, not just more compute inside them. The fifth is that AI deployment increasingly depends on governance systems built directly into products. And the sixth is that industrial expansion also depends on capital visibility and access. These are not 6 versions of the same theme, and not every signal originates in Asia. But together they point to a common shift. Technology competition is no longer decided only by who announces the fastest chip or the biggest model. It is increasingly decided in the less visible layers that determine whether those breakthroughs can actually scale. Coordination, integration, packaging, interconnection, compliance, and financing. For investors, that suggests a different discipline. Look past headline AI demand and ask where real constraints are forming. Watch whether the reported Apple TSMC DRAM issue is later confirmed or echoed elsewhere. Track whether memory pricing, capacity expansion, and utilization support Omdia's direction of travel. Follow whether Samsung's ZHBM and zNAND-O concepts advance toward commercial timelines, alongside V10 BV-NAND's rollout. Watch for AI-driven fiber projects to emerge in Asian markets. Monitor whether EU-style transparency requirements begin shaping AI product design more broadly. And track whether Vietnam's expected upgrade becomes official, followed by measurable changes in liquidity and foreign participation. The next phase of value creation may belong not only to the companies building breakthrough technologies, but to those solving the harder problems that allow the whole system to function.